Hello students, welcome back. Welcome to the second part of the chapter Organic Chemistry, some basic principles and techniques. So in the last video I have explained you about how this the name Organic Chemistry is associated with the study of carbon and its compounds, and I have also given a little information about carbon, the element carbon. So here carbon is the sixth element in the periodic table, and it has got 6 protons and it has got 6 electrons, and the mass number is 12. Okay. Now the electronic configuration of carbon is 1s2, 2s2, 2p2. Now here up to SSLC or in class 10th you might have studied about electronic configuration. The electronic configuration is nothing but it is a distribution of electron around the atom. So in any atom, so if you consider any atom in the periodic table, how you will be going to distribute these electrons in the atom around this atom, so that is called as electronic configuration. Now here in the carbon it has got 6 electrons, so this is distributed as 1s2, 2s2, 2p2, but you have studied it like 2, 4. So I know it will be like 2, 4, 8, 18, 32, like this it goes on. Now but here I have written like 1s2, 2s2, 2p2. So these two, according to this, the electronic configuration of carbon would be 2 and 4. But in PUC, in the +1 or +2 level, after this level, you are going to write the electronic configuration like this. So these two are, that is same, no problem, both are correct, but thing is that we have explained or we have specified that electron is present in the first shell, that is 2 electrons present in the first shell of the carbon and 4 electrons are present in the second shell of the carbon. Here according to this, the electronic distribution of electron in carbon is like that. In the first shell it has 2 electrons, in the second shell it has 4 electrons. But we are not exactly telling in the around this atom where exactly these electrons are present. But here using this you can tell where exactly these electrons are present. So it is like if someone asks where is Taj Mahal, so people may say it is in India. But if you want to tell exactly where the Taj Mahal is, so you will definitely say it is in Agra. So it is like you are telling that is electrons are present around atoms in orbits. But here a new concept is implemented, that is orbital. So we are telling electrons are present in the first orbit, and in first orbit the electrons are present in the 1s orbital. 2 electrons are present in the 1s orbital, and remaining 4 electrons they are present in the second orbit. But in second orbit the electrons are present in 2s orbital and 2p orbital. So in every atom, so there are different orbits. So if you can draw a carbon atom, so like this, the first shell will be like this. So in the first shell we have got 2 electrons in carbon, and in the second shell there are 4 electrons. So usually in two-dimensional you can write the structure of carbon like that. This is the representation or the distribution of electron in orbits. So this is the first orbit, this is the second orbit. But we don't know where exactly these electrons are present in this orbit. So here we are writing in the first orbit, these 2 electrons they are present in 1s orbital. So here comes a new concept, that is called orbital. So in the second shell there are 2s orbital and 2p orbital. There are 2 subshells, s and p. So in the second shell I will expand this. It has 1s2, 2s2, 2px1, 2py1 and 2pz0. 2pz0. Now here one electron from this 2s orbital will jump to 2pz orbital and it becomes 2pz1. Now clearly look into this. On the second shell we have two subshells, that is S subshell and P subshell. In the S subshell we have got one orbital, that is 2s orbital. In the P subshell we have three orbitals, that is known as 2px, 2py and 2pz. So now all these four outermost orbitals, they contain one electron. So about this electronic configuration you will study in detail in a separate chapter, but I have explained you this because when you are coming from class 10 or SLC, so you may get confusion about this. You may have some little confusion over this and this. So that's why I have explained you this thing. So whenever you are writing electronic configuration in PUC, you make sure that you are writing like this, not this one. So this is the correct format, but this is not accepted in PUC because we want more specific answers. Okay, so now don't apply these things for rest of the elements. You will come to know how to write electronic configuration for each element in a separate chapter, but as of now remember that the electronic configuration of carbon is 1s2, 2s2, 2p2, and in the excited state the electronic configuration of carbon becomes 1s2, 2s1, 2px1, 2py1, 2pz1. I think you are clear about this. So this is about the electronic configuration of carbon. Now when we are studying about the shapes of carbon compounds, we should know about the shape of carbon itself. So how this carbon is. Now I have told you that carbon in the outermost shell, it has 2s orbital, 2px orbital, 2py orbital, 2pz orbital, each contains one electron each. Okay, now this 2s orbital, it is not only for 2s, all the s orbitals are spherical in shape. Remember, all the s orbitals are spherical in shape. So I have written 2s, the shape of this 2s specifically for carbon I have written. So these things again you are going to study in a separate chapter. Still I will explain this a little bit. It is applicable to only carbon. So don't try to apply these things for other elements because it may not be perfect one. If you don't know about this in detail, you cannot apply all the principles of this to rest of the elements. So I am explaining only in the perspective of carbon. Okay, so in the perspective of carbon, if you see the 2s orbital, it has got spherical shape. So 2px, so it is not 2px, it may be 3px or like that. All these px orbitals or the p orbitals, they are dumbbell shape. They are the shape, they have these kinds of shapes. So I have written this 3 p orbitals. So these are the orbitals which I have written here. So the shape of these orbitals will be like this. The shape of these orbitals will be like this. Okay, so this is about the shape of these orbitals of carbon. So you are going to study the shapes of orbitals, the electronic configuration, and everything about orbitals in a separate chapter. But still, for your understanding, I am explaining this in earlier only for in the perspective of carbon. Okay, so now when this carbon is going to combine with any other element, or it may be with the carbon itself. So in order to form bond, so this 4 orbitals should combine with the other elements, right? So because these are the outermost orbitals. In these 4 orbitals, the outermost electrons are present. So we know that the outermost electrons are reason for the bonding of any element. So now the electron present in these orbitals, they are going to combine with any other element. Now when they are going to combine with any other element, so we can observe here. So here it is spherical in shape, here it has a dumbbell shape, all these are dumbbell shape. Now if this is as such, there is no bonding at all. So this cannot bond with any other element, because in order to form bond, the bonding orbitals, the outermost orbital should have same energy and symmetry. So it is like when a marriage happens, so everyone looks, if the boy is rich, so he marries a rich girl in most of the cases, because there is a symmetry, so there should be a balance between two sides, right? So that's how. So if these orbitals have same energy and symmetry, then these are ready to form bonds. So in order to form bonds, these orbitals, okay, so they are going to mix up each other, they will mix each other and they form a new hybrid orbital. Okay, remember, they are going to mix and they will form a new orbital, that is called hybrid orbital. If one s orbital, that means 2s, that is the number I am telling, 1s orbital and 3 p orbitals. So 2s orbital, that is a 1s orbital, I am considering number, quantity 1. So here p has 3 quantity. So these 4 orbitals they are going to mix. So then if they mix each other, then that is called as sp3 hybridization. If one of the one s orbital and 2 of these p orbital, if they mix each other and if they form a new hybrid orbital, then they are called, that is called sp2 hybrid orbital. If one s orbital, that is 2s orbital, and one p orbital, that is 2px orbital, if these two are going to combine, then they mix up and they become a new hybrid orbital, then that is called sp hybridization. Okay, so here this sp3 means 1s orbital and 3p orbitals, they have mixed each other and they become a new orbital called sp3 hybrid orbital. So here this sp2 means 1s orbital and 2p orbital, they combined, they mixed each other and they become a new orbital, that is called sp2 orbital. And when this happens, the energy of these 4, here we have 4 orbitals, here we have 3 orbitals, here we have 2 orbitals, because one from the s and 3 from p, so they are going to mix and they will give a new 4 orbitals, so that is called sp3 orbital, and all these 4 they have same symmetry and same energy. In this case, if before the mixing of these orbitals, s has different shape and different energy, and these 3 has different energy and shape. But after the mixing, all these 4 got same energy and same shape. Okay, so like that, here in the sp2 hybridization, we will get 3 hybrid orbitals of the same energy and same shape, and in the sp hybridization, we will get 2 orbitals, hybrid orbitals, that is of same energy and same shape. Now why this happens, I told you, it is to gain symmetry and same energy and symmetry, right? So now in order to form, whenever the carbon is about to form bond, this happens, this hybridization happens. Again, this hybridization with respect to other elements you are going to study in another chapter. So now I have explained you only about this carbon, and that is also whichever is required, only the part I have explained you is the necessary part for this necessary concepts of hybridization here. So you are going to study in detail about these hybridization in another chapter. Now in the methane, I will consider one compound, the compound of carbon, that is methane. So we need to discuss the shape of carbon compound. So I have considered one carbon compound, that is methane here. So methane has one carbon atom and 4 hydrogen atom. Okay, remember the two-dimensional structure of methane look like this, somewhat it look like this, but if you imagine this structure in a three-dimensional, it is like a if you consider a ball, then 4 hydrogen atoms are at corners. So there is one hydrogen, there is one hydrogen, one there and one there. So all these hydrogens, they are at the distance, maximum distance they can be. So they are present at the maximum distance of each other. So like that they present. Now in this case, in the case of methane, carbon, before going to form this methane, it should undergo hybridization. I told you, right? So whenever this carbon undergoes hybridization, it will form a new hybrid orbital. It will combine with it will mix up these 4 orbitals and they become new hybrid orbital. So here also it happens like that. So in the case of methane, I have written here. So this, the orbital I have written here. So this is a hybrid orbital. So or I can tell you that if I write like this is a hybrid orbital. Okay, so this is a hybrid orbital. Actual shape of the hybrid orbital may look like this, but if I write like this, it will be messy, it will not look good. So that's why I have written it here. I have represent this hybrid orbital like this. So you can see here 4 hybrid orbitals are there. Okay, so in the carbon you don't imagine the hydrogen now. Leave these hydrogens apart. So only the carbon, this is the center of carbon, then 4 orbitals. This is not in a plane, they are in the 3D space. Imagine this is in a 3-dimensional space. So if this is in the upper side, this will be in the lower, and this will be in the this side and here. So all these present in the 4 like this. So again this is not in a space. So they will be in the they present in the maximum distance. So whatever it is possible. So that's why if you just draw a line like this, you may get you will get one square. So if this happens, the bond angle will be 90 degree. But in this case, as they are in the space or 3-dimensional space, so the bond angle is 109.5 degree. So they will be they are present at the very different places. Now in the case of methane, the hybridization is sp3. In the case of methane, the hybridization is sp3. Okay, now here clearly observe 25% is the S character and 75% is the P character. Okay, because out of 4, 1 is S orbital. The contribution of S is 1. The contribution of P is 3. So that's why it is 25 and 75. So the new hybrid orbital which is formed after the hybridization is contains 25% S character and 75% P character. Okay, the shape of this molecule will be tetrahedral. So tetrahedral is nothing but I have told you. So if you keep one center in the space, so one atom here, one point here, one point here, one point here, and one point here. So all these combined, a spherical shape like this, that will be a tetrahedron. So tetrahedral shape. So that's how the methane will look like. Okay, the next molecule or the next compound I am taking is acetylene or ethene. Okay, now here carbon has double bond with another carbon, and it has a single bond with these two hydrogens each. Both of these carbon has two single bond with the two hydrogens. Now in this case, the carbon, each carbon, both of these carbons, they will undergo sp2 hybridization. They will undergo sp2 hybridization. That means one s orbital and two p orbitals will combine or will mix each other, and they will form a new orbital that is called hybrid sp2 orbital. Hybrid sp2 orbital. So here one p orbital remains as such. So out of these four orbitals, one s orbital and two p orbital will combine, will mix each other, and they will form a hybrid orbital called sp2, and this orbital remains as such. Okay, this will remain as such. So I have written in the diagram here. So this is a sp2 hybrid orbital, sp2 hybrid orbital. This is the sp2 hybrid orbital. Okay, so this is sp2 hybrid orbital. This is sp2 hybrid orbital. This is sp2 hybrid orbital, and this one is also sp2 hybrid orbital, and this one. So I have told you the shape like this is a hybrid orbital. This shape is a shape of p orbital. So this is unhybridized. So this is called unhybridized orbital. This is just a 2px or 2pz, I say 2pz orbital. So this is also 2pz orbital. Okay, now there is one bond between this sp2 hybrid orbital and sp2 hybrid orbital of two different carbons, and they will form one single bond here. Okay, but we have got two bonds here. This is because when they combine each other, so all these sp2 hybrid orbitals, they will be in the one plane. They will be in a one plane, and remaining this unhybridized orbital, that is like one lobe of this is above the plane and one is below the plane. Here also this is in a plane. Imagine these three sp2 hybrid orbitals are in a plane, and one lobe of the unhybridized orbital is above the plane and one is below the plane. Okay, now imagine two carbons are present here and here. Carbon atoms are present. Now this carbon atom has got three hybrid orbitals, that is sp2 hybrid orbital. So one is like this, one more is like this, and one more is like this. So here also carbon is there. So one will combine with the sp2 hybrid orbital of another carbon, and one more is like this and one more is like this. So this is in a plane, and the unhybridized orbital or the p orbit, unhybridized p orbital, present the one lobe. So here we have two lobes here and there. So okay, that is one of that lobe comes above and one of this lobe comes below. Okay, so here also one of the lobe comes above and one of the lobe goes below. So that's how the structure of this ethene is. So here this three hybridized orbital, they are in a one plane. In ethene molecule, you can see one head-on overlapping of sp2 hybrid orbital and sp2 hybrid orbital of different two different carbon atoms. So that forms one sigma bond here, and one more bond is due to the overlapping of unhybridized p orbital. So where is unhybridized p orbital? So this is the unhybridized p orbital. So they are going to overlap each other, axial overlapping or sideways overlapping. So they will form one more bond, that is called pi bonding. Okay, so this is how the bonding takes place in ethene. Now here, if I draw one lines between these hybrid orbitals, I will get a triangle here. So here also this is the triangle. So when we have 3 points or 3 orbitals, so the maximum distance they can cover, so they can present in maximum distance, so that is nothing but 120. If they are in 120-degree angle each other, then the maximum distance will be covered. So if the angle is above this or below this, then these orbitals, they will be near to that. Okay, so that's how this forms an triangle, and this both triangle are in one plane. Okay, they are in one plane. That's how the triagonal planar structure or the shape forms. So this is called triagonal planar, and between that triagonal planar, so this unhybridized orbital, they will form their one lobe will be in above that plane and one lobe is below to that. Okay, so this is about the ethene, structure of ethene. Now I will consider one more compound, that is ethyne or C2H2. Okay, C2H2. Here there is a triple bond between carbon and carbon. There is a triple bond between carbon and carbon. Here look at the diagram. Now here, in the case of ethyne, the hybridization is sp. Hybridization is sp. One s orbital and one p orbital is going to mix, and they will form a new 2 orbitals, hybrid orbital, that is called sp hybrid orbital. So here this in this ethyne, so this is the hybridized orbital. Okay, hybridized sp orbital. So that will form bond with that will have head-on overlap with the another sp orbital of the another carbon atom. So there is a bond, so that is one sigma bond, and another sp orbital. So now we know that in each carbon there is a 2 sp orbital. In each carbon there is a 2 sp orbital. Now out of these 2, one is bonded here, one had head-on overlapping with this carbon atom, and one more will be like this, and which will combine with the hydrogen, here. So this hydrogen, so that will be combined here. So this is how bond formation takes place. But here also same thing. Don't worry about this hydrogen and bonding. So I am just explaining about I am just focused on the shape of this compound. Okay. Now here the unhybridized orbitals. So in the case of ethyne C2H4, we had one unhybridized orbital, but in the case of this ethyne, we have 2 unhybridized orbitals. So in this case, the unhybridized orbital, they present parallel to the plane of this triangle. Here one is present parallel to this line, and one more is to the another angle. So if this is a plane, if this is the line, if this is the line of this carbon and carbon, so there is a carbon atom, so they will combine each other. One hybridized orbital will present like this. Okay, so one more is one lobe is above and one lobe is below. Okay, so here also one more carbon atom. So in that, one lobe like this, one lobe like this, one hybridized orbital, another unhybridized orbital will present like this. Okay, so you should have a imagination, you should imagine this in a three-dimensional space. So that's how the structure is. And here because these sp hybridized orbital, of course the maximum distance they can be have, so if they are in 180 degree, they will have maximum distance. So between these two hybrid orbitals, there should be a maximum distance. So in order to have that, these orbitals should be at 180 degree each other. Okay, so this forms a linear structure. The structure of this is linear. So this is about the shape of carbon compounds. Now I have I have told you many things about hybridization and all. So hybridization you will study in a separate chapter. Now here you have to focus on the shape of the carbon compounds. So shape of the carbon compound is important, and two little concepts are remaining. So that is hybridization influences the bond length and bond enthalpy of compounds. So now I have told you hybridization, sp, sp3, sp2 and sp. Now this hybridization, the change in hybridization also influences the bond length. How it influences the bond length? Because in the sp3 hybridization, in the sp3 hybridization, the S character is less, P character is more. That is 25% of S character and 75% is P character. So when there is a less S character and more P character, the structure of this hybrid orbital slightly it is longer, because P has a dumbbell shaped. Okay, and in the case of sp2, the S character is 33% and P character is 66%. Okay, 66.6 you can write, or 33.3 you can write. Now when you compare these two, here S character is more. When the S character is more, the bond length decreases. When the S character is more, bond length decreases. When the P character is more, bond length increases. So in the case of sp, the S character is 50%, S character is 50% and P character is 50%. Now these three in this hybridization, so you can have maximum or minimum bond length in sp and maximum bond length in sp3. As the S character increases, bond enthalpy also increases. Now change in hybridization affects the electronegativity of the carbon. So again this one more term, electronegativity. So you might not be knowing about this, but still electronegativity is nothing but capacity to attract the electron. When the S character increases, okay, that is the carbon atoms they form, they come to each other, or the bonding element, bonding atom, they will come to each other. So at that time the electronegativity is more. So this is about the shape of compounds. So if you don't understand what is sp2, sp3 and sp, so don't worry about that, because you are going to learn these things in a separate chapter. Here our main focus is to study the shape of the carbon compounds. Okay, so I hope you have understood the concept, and if you have any doubts you can contact me. Thank you.